Well, first off, thank you for having me at your lovely university. I'm excited to be here to speak about the death of computer forensics, which is a somewhat facetious title. And my secondary title is Digital Forensics After the Singularity. So how many of you are familiar with the sort of sci-fi concept of the singularity? A couple, a few, okay. I'll explain it in a bit. So my joke should become more clear. But first off, let me introduce myself. I'm a security engineer at Google, focused on incident response and forensic analysis. Previously, I've done work with Mandiant, you've probably never heard of, but they're a small consulting firm that does a lot of incident response work for very large defense contractors in the United States. I was with IBM X-Force Emergency Response and the United States National Nuclear Security Administration. I'm also the author of the just-released Digital Forensics with Open Source Tools. It's a fantastic book. I highly recommend it. And to clarify my background in the sort of cloud computing forensics world, I come from a kind of a standalone computer forensics background. So I approach this whole paradigm from that perspective. So my goal is to understand how the changes that cloud computing will bring about affect my work, and how I can keep doing what I've been doing, and how I can keep performing the sorts of examinations I've been doing. And alternatively, I want to know how to exploit the cloud and the sorts of advances it brings to enhance the work I've been doing and to make things better and faster. So I'm going to provide a little bit of background about computer forensics for those of you who aren't familiar with what we mean by computer forensics and digital forensics. So historic computer forensics involves the forensic acquisition of computers. That's the basis definition. This work grew out of law enforcement work in the early 1980s, late 70s, early 80s. I think the first US case that involved computer evidence was in the mid-70s. But the entire sort of computer forensics world that we exist in today grew out of this background of law enforcement-based examinations. And you can tell based on the tools and processes we use today. Most of them are single system focused, so you would have one computer system that you had discrete processing, discrete storage that you would seize, remove the storage from, and examine. And the tools and techniques are based on the analysis and recovery of file system artifacts that are either live or have been deleted. So again, this sort of belies the historical law enforcement background of computer forensics, what I term computer forensics. Notice I'm not going to be speaking about legal matters because I'm not well versed in Italian law. I know enough US law to keep myself out of trouble. So I know even less Italian law. So I'm not going to be speaking about legal matters. I'll be speaking in sort of generic terms about admissibility of evidence at a very high level. So when I discuss forensics, again, not to put a specific legal jurisdiction on it, but when we say forensics, we mean performed with the goal of admissibility in a court of law. Now, to perform a forensic analysis, we have kind of a handful of concepts that are universal across all jurisdictions that allow the admission of forensic evidence that I'm aware of. The process and tools that you use have to be tested. So you basically have to follow the scientific method. You have to have a theory. You have to experiment and test that theory, and then the test has to prove or disprove that theory. The process and tools have to be verified. So the output of the processor tool that you're using to extract data or perform analysis has to be able to be verified by a third party. It has to be repeatable, so if you perform the same sort of extraction or the same sort of analysis multiple times, you should achieve the same results. and the procedure has to be documented or documentable. So even if these other three kind of fly out the window because you're working on a live system, as long as you sort of document the processes you've taken, you should be able to defend the fact that you didn't intentionally alter anything that's of importance to the case in hand. And this isn't a checklist. This is just the sorts of the things that lead to forensic admissibility. So if you have most of these, you should be okay usually. And again, this varies based on the jurisdiction that you're in. Now, what is digital forensics and how is it different than computer forensics? Computer forensics arose from the sort of late 70s, early 80s police, law enforcement type of investigations. Whereas digital forensics is focused on the data that you're analyzing, not the devices that hold them. This becomes important as we move into cloud environments where you may not have access to the devices at hand. You may have only access to the data in a backend store. It also expands the scope of forensics to include any digitally stored data, not necessarily in a computer, quote-unquote, computer device. This is also important as more and more of the analysis that we'll need to perform falls onto devices that are not classically computers. So again, this expands it to all sorts of digital devices, any digitally stored data. This can include devices that actually aren't recognized as even like an internet device. It could be something like a closed-circuit television recorder used to record the scene of a crime. If the active files have rolled off of the accessible part of the system, you may need to be able to perform digital forensics to extract old video files off of this closed-circuit television hard drive. This is not something that would be recognized as a computer device at all. It doesn't have any users interacting with it. But again, we can use these same sorts of techniques if we expand our definition of forensics from computer forensics to digital forensics. It more accurately describes the work we perform today. More and more of the work we do is on analysis of discrete pieces of data and not entire computer systems. And it also future-proofs the terminology we use for the work that we'll be performing tomorrow, which is what I'm going to discuss in the rest of the talk. So the skills we use in digital forensics expand beyond the criminal investigations that I've sort of been alluding to that have driven computer forensics historically. I personally use digital forensics techniques in incident response primarily, so the live investigation of systems that are compromised or suspected to be compromised. Digital forensic skills and techniques can be used quite effectively in malware analysis and research. So you can actually discover every single thing that a piece of malware is doing to a system if you perform a forensic analysis of that system. And they're used quite extensively in civil litigation and legal discovery. So not criminal investigations, but still investigations to be used in a court of law. So one of the core principle of digital forensics is Locard's exchange principle. Edmond Locard he basically invented sort of forensic science as we know it today. Prior to this, almost all law enforcement investigations were based on eyewitness testimony and interviewing suspects. Edmond Locard came up with this idea that when two objects come into contact, they will leave traces of each other. They will exchange information about the other. So with contact between two items, there will be an exchange, is the sort of summation of this idea. And this is the core principle of all sort of forensic science performed today. If you touch a doorknob, you will leave fingerprints. If you step in mud at a crime scene, there will be mud in your boot and your footprint in the mud. This is also referred to in the digital forensics world as evidence dynamics. So this is the sort of motion of exchange of information between two things. So if you have a computer system that's compromised, for example, via a web browser, the compromised system will have web server logs and things like that, and then the attacker's browser will have evidence that it was on the computer. So they will exchange information as well. I also like to bring up the analogy of digital geology versus digital archaeology. So the item on the left is a naturally occurring rock formation, and the item on the right is a prehistoric altar created by people. Now visually they're very similar, but we have two complete distinct sciences that are involved in the analysis of each of these. So geology is the study of sort of autonomous functions of the earth and nature, so waves breaking at rocks and forming structures like the left. Digital archaeology is the study of the effects that people have on their environment, the items on the right. The digital equivalence of these, digital geology is the portion of data forensics that involves the artifacts left by autonomous system activities. So these are things like inodes, block groups, things like this that the user doesn't actually have any sort of interaction with. It's just something that the system uses for internal housekeeping. This is audit logs and things like this. Whereas digital archaeology would be the study of things that the user is actually creating. So documents, images, things like this that the user is actually creating. And we can perform forensic analysis of both sets of data. I'd also like to talk about a few different sort of data archetypes. So we'll have three archetypes of data that are sort of recurring as we go. There's the data at rest, which is data that's stored on hard drives, floppies, CDs, DVDs, thumb drives, these sorts of things. And this is classically the domain of computer forensics. When people would perform computer forensics, this was the entirety of the data that they would usually examine. Next, we have data in transit. So this is data moving from one location to another. This is the domain of network forensics. So this is traffic being generated by two systems communicating over the internet. And third, we have data in execution. And this is the domain of memory forensics. Digital forensics encompasses all three of these. So this is why it's kind of a superset of computer forensics, network forensics, and memory forensics. So to kind of visually explain the sorts of things I've been talking about so far, let's say for an example we have a thumb drive that has an Excel spreadsheet on it. The thumb drive is put into a standalone PC, and the Excel spreadsheet is copied to that PC. Later, the user of that machine uploads that Excel spreadsheet to a web service that lets you host Office documents. Let's say Google Docs, for example, is one that I'm familiar with. So at this point, the activity that's been performed has created traces on disk. The network activity has created traces if there was a capture being created, and then there's been some sort of execution of code in memory and on the processor. And on the back end, the web server translates the spreadsheet into a binary blob, inserts it into a database of some sort. The database says, yeah, everything's okay, sends an okay message back, and then that's transmitted to the user. So this is what you would examine if you were doing regular computer forensics. You would examine the traces between these two. If it's a Windows system, there would be registry artifacts of the USB key being inserted. If you found the USB key, you could prove it was the same USB key for the most part. There would be shortcuts created if the spreadsheet was opened. This would be the domain of memory forensics. So if you had a memory snapshot of the exact moment that this was being transmitted, you would have local artifacts in memory of the network connections, the sockets that were opened, and you would probably have a copy of the spreadsheet in memory. And network forensics would get you this piece, the transmission of the data from the local system to the remote end. In addition to the three sorts of archetypes I've talked about, there's a couple sort of specific focus areas of digital forensics that I'm interested in. One is you could perform analysis of the Excel spreadsheet itself. It can carry information about the system it was created on, the user that last printed it. It can have embedded dates, things like that. So the actual file itself can carry forensically interesting information. And this is what I call file forensics or file analysis. And then the database actually has internal housekeeping that it performs when it actually makes, most databases will have sort of transactional information that's created when changes are made. And so even if the change is not completed or it's later deleted, you might be able to find forensic information in this realm, and this is database forensics. So these file analysis and database forensics are kind of emerging areas. So I have a few caveats when I talk about digital forensics. There are quite a few differences between corporate/managed legitimate access at law enforcement type forensics that I mentioned before. Obviously, I speak from a corporate managed access background. The point is, I usually have legitimate access to the systems that I'm examining. If you're law enforcement, you may not have, when I say legitimate access, I mean from the system's perspective, not that law enforcement people are running around rampant, stealing computers and analyzing them without permission. So when I say legitimate, I mean, as far as the system is concerned, you are a legitimate user on that system. So when I examine a system, I am a legitimate administrator on that system. So I can do a lot of things that you normally wouldn't be able to do if you're coming from the view of an external party. So like I said, law enforcement forensic examinations generally don't have legitimate system access as far as the system is concerned. So security features designed to prevent hackers and other external adversaries from gaining illegitimate access to your data will also hamper law enforcement examinations usually. So this is things like encryption on the disk or things like that, TPM, any of these security features that are supposed to prevent malicious third parties from getting at your data can also hamper law enforcement investigations. I'm going to bypass most of that because this doesn't really affect me that often. Another caveat, I'm speaking from the perspective of somebody from the United States, in case you couldn't tell by my outrageous accent. So getting back to the title of my talk, the singularity is a technological the technological singularity is a hypothetical event occurring when technological progress becomes so rapid that the future after the singularity becomes qualitatively different and harder to predict. What this means is, as technological advancement becomes more and more rapid, things change faster every single day as we move towards the future. The singularity is that point in which we are living in the future. It's sort of a theoretical point in time that we won't really know that we've crossed until we've crossed it. To kind of visualize it, the x-axis we have time, the y-axis we have technology. This is the curve. This red line is the singularity. We are here, maybe. And we don't really know what will happen once we cross this threshold, except that there are dragons and robots that want to kill us all. So a lot of forensic examiners are very scared of the cloud. The cloud is going to kill forensics. We're all going to have to find new jobs, and I don't want to find a new job because I'm not good at anything else. So these are some of the previous things that were supposed to kill computer forensics. Bigger hard drives, encrypting file systems, virtual machines, U3, bootable thumb drive type things, and then private browsing. These all were supposed to kill forensics, and I should have been out of work a long time ago. So the things we did to survive so far. Bigger hard drives, we survived these by getting even bigger hard drives. This is the sort of, they bring knives, we bring guns. We survived this by using better data reduction techniques. So we were able to focus only on the data that matters, data that's changed, data that we don't already know about. And we were able to survive this by more processing power. This is the Google solution. You just throw more processors at them. It helps when you have infinite processors. Encrypting file systems, we survived by capturing image of the system live. So if the disk is at rest is encrypted, you just wait until it's decrypted, and then you get an image of it then. It's pretty easy. And in the corporate world, we survived this by having legitimate access to the keys. So it's not really a problem for us. For law enforcement, I can see how it might be a problem. Virtual machines, we survived by embracing them. We love these. These are great. It's a tiny, tiny hard drive image. Usually it's sparse, so all the the data that's allocated is data that's interesting. They usually have memory snapshots because they're suspended, so these are great. I don't know why people were afraid of these. I love analyzing virtual machines. You can script it. You have 20 virtual machines on a system. You can just run across them, find things that are different. It's great. Bootable thumb drives and U3 sort of things that we're supposed to have applications that existed only on the thumb drive and we're supposed to not leave any traces on the system. They don't work. They leave traces on the system. So that was not too hard to survive. They'll leak the path of the file that was executed. They'll create shortcuts. There's all sorts of things. This includes things like TrueCrypt volumes on external drives. It'll leak paths into the TrueCrypt volumes. So this is on Windows systems. It's pretty easy to figure out when things like this are going on. And private browsing modes, I don't have a good answer for this yet. I'm still doing research, so talk to me in 3 months or so, and I might have better information on this. So so the title of my talk, The Death of Computer Forensics, is sort of facetious. Computer forensics won't die per se, but if you keep doing exclusively computer forensics, your career will die. Computer forensics is becoming a subset of the larger discipline of digital forensics, which I've discussed. And our goal at this point as examiners should be to take the things we've learned during the era of computer forensics, take those same techniques and apply them to the changing landscape before us. So I've identified sort of 3 major changes coming up that I think are going to affect digital forensics quite a bit. The first, these are the things that are going to kill forensics next, but they aren't really going to kill them. We'll be okay. So the first is flash media, so SSDs and things like this. The second is the explosion of devices, digital devices. And the third is the cloud. And these all sort of tie together, and I'll explain that as I go. So the structure I use for the rest of the talk is for each section, I talk about how things worked prior to today, so yesterday meaning an arbitrary time period, 10 to 20 years in the past. I talk about how things work today, and then I talk about how things will likely change tomorrow. And then I'll explain some of the benefits we get from the changes that are coming up and some of the challenges we need to overcome. Now, when I have to caveat, when I talk about things that are happening tomorrow, none of these are upcoming Google products, none of these are feature promises. This is just me sort of pontificating based on no internal knowledge of anything at Google. So the first new killer is flash storage, the birth of cheap flash media. So prior to today, yesterday, everything had rotating hard drives, they had cylinders, sectors, heads, this whole sort of thing. If you're familiar with kind of fixed disk storage, this is all pretty basic. But forensic examiners love these because they understand them for the most part. They understand them because they've been pretty much the same thing for about 50 years. So they've had a long time to kind of get to know these and understand how they work. They really haven't changed all that much in 50 years, except they got smaller and denser and cheaper. And then they put a little bit of memory on them, and they started remapping some sectors. But other than that, they've remained basically the same internally for about 50 years. Now, in the good old days, file allocation worked a little bit like this. This is a generic proto file system. If you've taken any file systems class, this is probably like ext0, which is a theoretical junky file system I just made up. But this first column is directory structure with file names in it. The next column is your metadata structure, so an inode or MFT entry or something like that. And then the rest is blocks that are allocated to the file. Right. So the directory entry has a file name, file 1. File 1 points to the inode. The inode has the inode number. It has a date. It'll have other metadata, which I didn't put in here because it's not important for this. And then it'll have the size of the file and the block structures that are allocated to it. So each one of these little green squares, or these little squares here, represents a sector on a hard drive. So this is 512 bytes. So each one of these rows is one cluster or block, depending on the file system you're using. So this is pretty simple. This is file allocation. We write a file. We write a bunch of blocks out. Da, 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 da. The gray blocks are in unknown state right now. Pretty basic. Every forensic tool, every forensic examiner knows this. Well, not every. Everyone should. Every forensic examiner should, but I should probably back that up. You know what I'm talking about. So this is fairly well understood. And this is what happens when you delete a file. That was probably pretty hard to see because it was quick. So watch file 1. Bloop. So that's it for the most part. Depending on the file system, things will get a little bit more complex. But the file entry, the directory entry with the file name is unlinked. All the other structures remain in place. This is how undeletion works. This is how forensic recovery works at one level. So this is pretty easy. This is really fun. This enables the bulk of forensic recovery. So that's easy. Another way that this process can get a little bit dirtier is in some file systems, the link to the clusters or the blocks is removed when you delete a file. So all the pieces are still there. It's just putting them back together is a little bit more difficult. So again, that's all pretty easy. We've had it pretty easy up to this point forensically. Also in the good old days, we had a thing called slack space. So these are the blocks allocated to file1.txt. Later, file2.txt is written after file1.txt is deleted. But in these last 4 sectors, sectors of file1 text. So we can recover information out of here. If it's raw text, it's great. You might recover information from swap space or page files, things like that in here. So this was another kind of previous source of forensic information that we had access to that we don't anymore coming up. So today, instead of fixed disks, we have kind of an explosion of flash and SSD. So when I say flash, I mean any sort of non-volatile memory used as a persistent data store. So this includes things like thumb drives. This includes things like compact flash. They're great. They're very dense storage. They're very low power consumption, and they have no moving parts, which makes them great for things that move around a lot, like phones. You don't want a hard drive in a phone in your pocket. It'd be loud for one. It would be hot, and it would drain your battery really fast, and it would break. Solid-state disks are the flash-based replacement for traditional hard disks. So basically, they're an array of flash chips on a controller on a board with a drive interface. So how will these impact forensic analysis? So today, the allocation of a file on flash, again, and this is like sort of generic and high level, but the allocation is pretty much the same, except you notice previously where we had gray blocks that represented sort of an unknown state, now we have white blocks which are null, those are empty. So with flash, we'll never have slack space, basically, and I'll explain why in a little bit. So that's one sort of major problem. Flash is also allocated in pages. So we have sectors here, but that's not really how things happen. So flash is allocated in pages. So you have page 410, page 411, page 412. Each sector, each one of these represents a sector, but the flash will only allocate them in groups of 4K at a time, usually. It's usually 4K for most flash that I'm aware of. And it also, any sectors that are left over will be blank, basically. So one of the problems with flash is there's a couple problems involved in writing over and over to the same cells. So they'll wear out pretty quickly, depending on the flash and who you talk to and what vendor is trying to sell you flash. It'll be anywhere between 1,000 and 100,000 writes or something like that. It's probably closer to 1,000. So basically the sector or the pages internally will be remapped on the fly. Subsequently, these same 3 sets of pages will be remapped to these random assortment of pages, and then there's a table that kind of keeps track of them. So this is pretty complex if you ever try and do file carving on the raw level, because the blocks are sort of remapped randomly, which is unfortunate. So that's one complication that it adds, but the deletion, the state of deleted data on flash is actually, it's either amazingly good or horrible for forensics. and I'll explain why. So this is the first option for deletion on Flash media. So we can only write a page at a time, which is usually 4K. We can only erase a block at a time, though, on Flash, just because it's sort of an internal artifact of the way Flash works. So it can only erase a block at a time, and it attempts to even out writing to cells. So the first time, this is version 1A of a file that gets written to page 412, and then 1B gets written to page 902, and then 1C gets written to page 1123, and then 1D gets written to page 108. Depending on circumstances on the disk, all four of these versions could just exist out in Flash at some point. So historically, on older Flash, like on feature phones, like kind of Nokia flip phones or older Motorola phones, things like that, you would have this sort of a journal of changes, especially for things like FAT directory entries, things like that get written over and over. You would have a history of changes kind of spread throughout the Flash, which is pretty nice. It's helpful for forensics because you get like this huge litany of unallocated data. So that's great. If it just did that, that would be awesome. Unfortunately, this wears out drives really fast, and it's ugly, and it makes writing slow. So the other option is so let's say we have this Flash. This time, instead of sectors, each one of these represents a page. So each one of these is an allocated page. The white ones are unallocated. And so this is pretty full, so we need to do some housekeeping. So we delete some data. So prior to the garbage collection and trim that SSDs do now, these gray ones would be in an unallocated state, but you would still be able to recover data from them. So to increase the performance of SSDs, there's a couple different methods that drives use, but they're sort of all gravitating to trim. So garbage collection implemented by different SSD manufacturers would happen sort of in the background, and then trim will happen. There's an ATA call you make, and it'll do it on demand. But basically, it clears the unallocated space to speed up further writes. So this is what happens to all of your unallocated space on the drive. It's blank. So the garbage collection does this in the background. Trim does it on demand. Both of them usually happen within a couple minutes. So it's quite unfortunate if you're trying to recover data. It's also quite unfortunate if you happen to be hashing the drive at the time the garbage collection is going on, because it'll change as you go. So this is actually fairly disastrous for the recovery of unallocated space. So tomorrow, what will happen, this is again me just sort of pontificating and looking into the future. Rotating disks, I think, fixed disks, regular hard drives, we'll see a decreased use for end user devices. Even devices that aren't necessarily mobile, there won't be physical hard drives and things for the most part anymore. This is because power consumption and size, you can make devices with SSDs on Flash much smaller, and they draw way less power, they're quieter, and they don't generate as much heat. But fixed disks will continue to be used for bulk back-end storage, things that need lots and lots of space. We'll still see this because they're cheap for the amount of storage you get still. I also think we'll see an increase, at least in the corporate and government world and military, of self-encrypting or self-wiping drives. There's new drives coming out that basically mate the hard drive controller with the device that it's built into, usually using TPM. There's some proprietary things that also do this, but it'll mate to the board. And so if you take the hard drive out of the system and try to hook it to another system to do a traditional forensic acquisition, the drive will either wipe itself or it will be just encrypted at the board level. Or it can also just prevent access to specific blocks in the file system. So I can see this will be increasingly popular in the corporate world. I don't think end users will have much use for this because I think the risk of losing your data completely outweighs the risk of somebody possibly stealing your data. But also, we have this sort of disastrous automatic wiping that occurs on SSDs. Pretty much all SSDs nowadays, and more frequently, every SSD will do this. But this is actually sort of counterbalanced by operating system features that'll basically kind of slow down it'll slow down data from actually entering a deleted state. So the SSD wiping only occurs once the operating system is freed or once the file system has freed the blocks. So the three kind of major consumer operating systems are all either currently or they will very shortly have snapshotting features that sort of prevent blocks from being freed. So on Linux and Solaris, Linux currently has LVM snapshots. These are not super great, but they basically create a fork of the file system at the time the snapshot is created. So these can actually prevent the blocks of a file from being released back into the freed pool. So that actually slows down this sort of trim thing that might happen. And these are at the block level. BTRFS is an upcoming Linux file system. It's available in the most current kernels. It's still beta, I think, but it's supposed to be the next replacement for ext whatever. And this actually supports snapshots with rollback. So again, this is another thing that keeps blocks from being freed, and so it should prevent this sort of disastrous trim wiping. And then ZFS is the sort of default file system in modern Solaris, and it also has snapshots and rollback. I was going to say much like BTRFS, but I think BTRFS had them after. So, but it has the same sort of feature set of this function that prevents the blocks from being released. Windows system, Vista Server 2008 and 7 Plus have volume shadow copies. This is, again, block-based file system snapshots. It replaces the restore point functionality from older Windows versions. And shadow copies are basically, they're like sub-volumes that are created at block level, and they're created automatically. So every, I think it's 12 or 24 hours. And then on specific events, so when new software is installed, new drivers are installed, it creates a volume shadow copy. And so you can have 14, 15, 16 volume shadow copies on a system at a time. And remind me not to touch that over there. So those actually, because it's block-based, those blocks are still considered allocated by the file system, and so they aren't released back into the freed pool to be overwritten. And so a forensic experimentation with volume shadow copies is ongoing. Right now, we can get access to these, but we have to do it via Windows system, and we have to use Windows system administration tools. It's not very forensic-y, but it works for now. Forensic-y is a technical term forensic people use. And on OS 10, there's a couple different snapshotting mechanisms. Time Machine is the current one, but it requires external media. So the user actually has to do something, which no users actually actively back up their data. It just doesn't happen. You have to physically plug a drive in. And it makes your Mac look ugly because you have this drive hanging out. So nobody does it. But it's a file-based, which is another problem with it using hard links. So if you have like a 4 gig file, like if you're on a Mac, you're doing video editing, you have a 4 gig file, every change to that file requires backing up the entire 4 gigs. So that's kind of a pain. The next version of OS 10, it's like Cyber Jaguar or whatever it's called, some sort of big cat. Don't know what, but it has a feature called versions, and so this is auto-save file snapshots, and you can actually manually create snapshots as well, and these are file-based, and I believe it's at the block level, and you can either create these manually or it creates them hourly. So this is again in the upcoming version of OS 10, so this will require some forensic experimentation to figure out exactly how this is working, but this could be a really good source of kind of archived forensic information. And again, this is something that prevents the blocks from being released back to the system, so it actually stops this SSD auto wipe. So technology taketh away on one hand and giveth back on the other hand, which is pretty nice for us. So the things we gain from the expansion of flash media, there's not a ton of sort of forensic benefits now that the kind of archived block history is gone. But we get speed, reduced power consumption, reliability for devices. We have the possibility of greater security against unauthorized access with this sort of encryption and security being moved onto the board. We have possibly more trustworthy sanitation of sensitive data until somebody releases a groundbreaking paper about how easy it is to recover information that's been overwritten on an SSD. I don't think that's happened yet, but I'm sure somebody will. But for now, things are great. And we get, again, the things I talked about with file system features preventing blocks from being released back into the pool to be deleted. So the things we need to be ready for with this change is that in some cases, just providing power to a drive may cause data loss. This could be because of trim. This could be because of security features on the drive that say if I'm ever powered up outside of my host, wipe me. So that's just something we need to be aware of. And again, the on-disk encryption and wiping capabilities as well. And we also need to be aware of these file system snapshotting capabilities I mentioned and the possible forensic data that will be present in these snapshots. But moreover, we need to be able to perform defensible live acquisition so we can bypass these sort of hardware or these low-level problems of interacting with fumbly bits and weird hard drives and things that might be erasing themselves by just performing an acquisition live on the system and being able to present that as the best copy that's possible to get. So the next sort of major change that's going to affect forensic analysis is the kind of explosion of digital devices. These all happen to be Android-powered devices, but I'm not a salesman. So, but again, these are sort of 4 different types of devices. And more of the sort of interaction with the internet and other services that people perform are going to be through devices like this, and they're going to be less common on kind of classical computer devices. So yesterday, we had sort of 3 divisions of systems. We had desktops when people needed power, speed, and drive capacity. We had laptops that were slow and junky, but they could move around. And we had servers, which were what IT people ran, and us users didn't know anything about them, except that's where your exchange mail lived. And that was the good old days. Everything was great. So these 3 sorts of systems were basically all the same things. They're built out of the same stuff. So they used fixed disks for storage. That's data at rest. They used standard x86 processors for the most part. That's data and execution. And then they used wired network connections. You had to plug into the wall, and that's your data in motion. So they were basically different assemblies of the same sort of core parts, more or less. So today, we have this sort of explosion of devices. So mobile phones, I put in quotes because your phone does a lot more than your laptop did 5 years ago. And tablets. Basically the kind of market for PC shipments has peaked at this point. Basically everyone who has a computer, or everyone who wants a computer has one already. So the market I think shrunk 3% for PCs and laptops worldwide last year. So those will continue to decline, I think. So yeah, your phones are capable of many things beyond just simple phone calls that you guys are all aware of. Audio is still motion, and they're constantly connected, which is another thing that makes them kind of better than most sort of classical computing devices in that you can just access your information online all the time. And there's also this sort of relatively recent expansion of netbooks, which are basically just small laptops. They're not really any different than other laptops, except they're smaller. And then kind of pure netbooks, like things running Chrome OS, which is another Google project. And these are, I'd say pure netbooks because like Chrome OS netbooks are basically worthless unless they're connected to the internet. You can't really do anything offline with them. So those are much more sort of pure internet devices. The things these all have in common is they're not designed to be taken apart. So that sort of breaks the kind of classical computer forensics model of grab a system, remove the hard drive, take the pieces out, da 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 da. So this is all one sort of monolithic unit. It's a consumer electronic device. It's not a computer, but it's the uses that people are using them for are replacing most of the functions that they've previously used computing devices for. So moving beyond sort of phones and tablets that we're all aware of, there's even more sets of electronic devices that can be used that can either be possibly compromised in an intrusion, or they can be used as part of a criminal case. They can be used for nefarious purposes. So game consoles, every single game console currently sold today has internet capability. They all have some sort of embedded storage. And then so they have the capability to move data, they have data at rest, and they have data in execution. So they have all the same sorts of criteria for all the other things that we talked about with data forensics. Blu-ray players are all networked. Most of them are networked. Most of them can be firmware upgraded over the internet. So again, they have modifiable local storage, and they have network capabilities. And then we have pure video streaming devices like the little Roku streaming devices and other things like this. And then we also have more televisions that have video streaming built into them. So again, these are things that transmit data from one place to another. They interact with services, so they could all be of value during a forensic examination, depending on the scope of your exam. And even today, our actual computers are more and more device-like, right? Like these are technically computers, but they're really consumer electronics devices. You're not going to disassemble this beautiful Mac, right? You can't take it apart. You'll get in trouble. The magic will fall out, and it won't work anymore. So again,
take it apart, but it's done for very little rest.
Yeah. You don't want to take it apart. It's a one-way operation. You'll have extra pieces. So tomorrow, for people on the go, they'll be using almost exclusively, I think, smartphones and tablets. Maybe netbooks and sub-notebooks. That's still up in the air of if that's going to go anywhere. Or more likely, I think, tablets with attached keyboards or detachable keyboards, if you still need the keyboard form factor. But I also think the expansion of smartphones and tablets is going to come at the expense of traditional systems, especially in emerging economies. So this is an Idios U8150. It's available for $100 US, so it's running Android 2.2, I think. So it's an actual full-featured smartphone for under $100. A couple years ago, there was a very well-publicized project to create the world's first $100 laptop for, everyone in India can have their own laptop. Well, now they can all just buy their own smartphone and have even better functionality because it's always connected. They don't need a $100 laptop. This serves all the same purposes and more. I think at home, the home computer will sort of fall by the wayside, much like the home telephone is today. The home computer will be kind of an antique device, right? Because your mobile devices do everything you need to do that your computer has historically done. This will also serve the secondary function of extending the lifespan of existing computers. So I don't think people are going to go home today after hearing me talk and throw away their computer. But I think by and large, the computer that they have right now is going to be the same computer that they have in a year or two. They're not going to buy a new computer every 18 months unless they're a hardcore PC gamer. And good luck to both of you. This is also sort of interesting too, because as people who design web services build for embedded devices and mobile devices, these are usually slightly lower powered devices. They're not quite as featureful. So your existing PC actually gets additional life as people design for mobile, because you don't have to get a bigger screen, you don't have to get a faster processor, because websites become more accessible. I think we're going to see the growth of kind of cloud-dependent and subscription-based streaming devices. So this is like Netflix streaming, things like that. It'll be things like the Chrome OS netbook, where it's kind of useless unless it's paired with some sort of online service. I even think we can get to the point where this is sort of subsidized, right? Like it's you sort of lease a computing device as part of service with a certain provider. And these won't have any local storage at all per se. They'll have like a boot ROM with embedded flash or something like that, but they won't have a disk for storage. They'll stream everything, and they'll have a fixed amount of memory for cache. Again, this won't be for everybody, so there'll be a certain level of power user that wants some sort of local storage for archive. They want to rip all of their vinyl albums to lossless encoding and listen to them on $10,000 headphones or whatever. So there'll be those people, and they'll have giant storage networks. But again, that won't be a computer per se, because it'll be running an embedded OS that you interact with, like your wireless router today with a web interface or like a little touch panel on the front. So it won't be sort of an interactive computer device. Like it'll be a feature-driven single storage unit. And then again, computers won't vanish completely, but because certain classes of people will still need high-end workstations. So audiovisual people, writers, coders, etc., will still need like all of their storage, all of their processing, and all of their network stuff to be fairly close to them. So there'll still be high-end workstations for those people. In the workplace, legacy laptops and workstations will still, the workplace will lag behind, so you'll still get a laptop at work for the foreseeable future. But again, I think there's classes of workers that will exist entirely on kind of mobile embedded devices. So this is like remote salespeople, field operations people, these sorts of folks will work entirely on sort of embedded devices. In the I think the workplace will be one of the places that's driving the adoption of kind of pure virtualized environments and cloud service. So the things we gain from this move to embedded devices and mobile devices away from kind of classical end-user modifiable computing devices is we have a powerful portable device that's strongly tied to a single user. So at least in the Western world, your phone is your phone, right? Like previously there was the phone, which was in your house. Wow, you guys probably don't remember. But at one time, your grandparents had a phone that was wired into their house. So, so that was the phone. So very recently, that became my phone, and that's your phone that you carry with you. So it's a personal device that you have. And so as a forensic examiner, we can kind of a priori assume that most activity on that device is going to be you. So if it's your phone, by and large, you did it, unless we have some other extenuating circumstances that make it appear that you did not. From a defensive perspective, mobile devices are arguably more secure or securable. I say arguably because people like to argue about this. This is due to things like sandboxing, code signing, etc. And this isn't necessarily intentional. I don't think the people who make smartphones intentionally set out to make them more secure. They set out to provide digital rights management so you couldn't put wares on them. So, but you have the side effect of, because you can't install unauthorized software, you get a side effect of extra security because any sort of malicious software would either need to do a secondary sort of security exploit, or it would have to be signed and be legitimate software. One of the other benefits of the use of embedded devices and these sorts of mobile devices is it's possibly more difficult for the user to sanitize artifacts, especially if it's things they don't know are there. I haven't seen anything like evidence eraser on Windows. I haven't seen anything like that for any sort of embedded system or phone system. So it's probably a matter of time until that occurs, but for now, there's a sort of whole slew of artifacts that are generated on phones and tablets and things like that that the user either doesn't know are there or can't actually do anything about. And in the short term, until we enter this pure magical post-PC world that Steve Jobs talks about, PC to device artifacts will remain valuable. So this is things that actually transfer over, like when you sync an iPhone to a computer. Again, we have this sort of evidence dynamics of data from the computer moving to the phone and data about the phone moving to the computer. So those will still remain valuable as far as I can see for the future. And we have these sort of convergence artifacts that are created. So they're brand new classes of forensic artifacts that are created due to the fact that you have this sort of unique device that has all these functions in one thing. So you have video recording, camera capture, a GPS, you can make phone calls on it. So when you take a picture with your iPhone, it embeds the GPS coordinates of where you took the picture in it. So again, that makes a picture of a location more legitimate. So if you have a picture of a location and it has GPS coordinates of a location, you have a higher bar of proving that yes, this picture was actually taken in this location and wasn't doctored. So the things we need to be ready for with these devices forensically, we need to realize that physical access to the device that as we've understood it historically for computing devices may not be available, or it might be undesirable. So to get kind of a classical forensic image of an iPhone or an Android phone, for example, you have to disassemble the device and desolder all the chips and hook them up to a chip reader, and it's sort of a one-way operation, right? Like you can't take someone's phone and then do that and then give them a bag of parts back and say, here you go. I mean, in some jurisdictions maybe you can, but it's frowned upon, I'm sure. So because of this, we have to understand that possibly the only activity log we might have of a device doing something is on the remote end. So whoever the provider for the service in question is, they may be the only ones that have the logs of a certain activity on the mobile device. And we have to understand what those logs will be and where they live, and if we can get them. We also have to understand that the device may not actually hold the data you seek. So for something like a Chrome OS netbook, there's literally nothing of value on the device that you can get forensic. Everything is in cloud services. The device itself has a very small amount of flash, and there's just nothing of importance on it. So given this, if you run a managed infrastructure, make sure that on-device and off-device logging is appropriately robust. So device check-ins, things like that. Make sure you have the logging infrastructure that you need to determine what's going on with your devices. And at the very, very minimum, ensure proper device management. Again, this is for kind of corporate managed infrastructure. But the very minimum, a managed device should have remote lock and remote wipe. Because otherwise you have a mobile device that can get access to your kind of internal infrastructure and it's floating around. So the third kind of harbinger of doom for forensics is the cloud. So prior to yesterday, we have the laptops, desktop servers I talked about before, and they each have their own local data store, a little hard drive inside, and all your data is fragmented around. This is fragile because if you have a single desktop with a hard drive in it, and that's your only location for a critical report, hard drives tend to die. So then that data is gone. It's also dangerous because if you have, for example, a laptop that has the critical report on it, laptops tend to wander off, they get stolen, and so this data is the only place you had it, now someone else has it and you don't have it anymore. And so these systems were sort of artificially partitioned. They couldn't communicate directly to each other because of this lack of ubiquitous connectivity. So this makes data sharing difficult, data sharing between different parties, data sharing between different systems. And it also makes data synchronization difficult. So you have two copies of a file, one on your desktop, one on your laptop, and you edit one, and it's out of sync with the other. And there's a third on the server, and so you have to keep these manually in sync. So there's all sorts of code checkout systems that fix this, but they're all sort of onerous. They add their own problems. So you have different forks of files and things like that. So today, we're sort of living in the beginning of the cloud era. So all these technologies I mentioned before, flash storage and mobile devices are in sort of a feedback loop with the cloud. So we have robust, portable flash storage, and that's one of the key technologies that's enabling mobile devices like smartphones. So, and smartphones are increasing in power and they're increasing in reach due to kind of always-on connectivity, and other sort of similar devices. like tablets are enabling people to use cloud services more and more because you have a device with you all the time that's always connected. And so that's increasing adoption of cloud services like Google Apps. And then as these applications become more and more robust, they become a more and more useful replacement for traditional desktop applications. And so then that drives, so the Flash drives mobile, mobile drives the cloud, and then the increase in features of cloud services drive the adoption of more and more mobile devices because your mobile device is more likely to be a replacement for a traditional desktop. And then that drives further innovation in the Flash media. So besides the sort of corporate or business applications, there's this whole other kind of explosion of consumer media applications driven by the cloud. So, I mean, there's tons and tons of Blu-ray players and things like this that all have Netflix streaming embedded in them. Every single smartphone has YouTube streaming, and this little guy on the right is actually something I own. It's an online gaming service, so the game is actually streamed remotely from a data center. So this actually works pretty well as long as you're physically close to the data center. So that console is about the size of a pack of playing cards. So and all it does is stream. It has a video decoder and it streams over the network. So even things that were classically required of a fairly beefy local machine can be done entirely over the network. So as we see the cloud sort of expanding in the business world, this means the physical server as a unit of computing is kind of deprecated. All you really need to perform computing functions is storage, which is torque, cycles, which is horsepower, and throughput, which is top speed. So, and these also map to data at rest, data in execution, and data in motion. So that's really, to do computing, those are the three things you need, and this is what I've been talking about the entire time. We have these three sorts of data. And so with the cloud, businesses have the capability to immediately grow capacity. If you need more cycles right now because you're a front page story in the New York Times, you can do that. Or you can actually reduce the size of your fleet if it's a slow season. So if you're like an online retailer, during the holiday season, you can expand your computing power, and during off seasons, you can reduce it. And because of this sort of, because of the way businesses use cloud architecture, many traditional IT problems are reduced or eliminated, but they're really just abstracted or abdicated. So your IT problems just get pushed further away. So they become someone else's problems, which is good. So we have three types of clouds by segregation. So we have a private cloud, which is you set up a bunch of servers, you set up a bunch of physical machines, and you set up your own sort of cloud services for your organization or your company. And then there's the public cloud when you push all that off to a third party like Amazon or Google. And then there's the hybrid cloud, which is some combination thereof. The other way you can classify the types of clouds is by function, and this is probably more valuable. So we have infrastructure as a service, and this is something like Amazon EC2. Rackspace has a similar service. So this is, you get virtual machines, you get virtual networking, and you get an operating system, and you get dropped to a console. And so then everything else, all the applications, everything else, you have to write yourself or hire somebody to write. The next higher level of abstraction is platform as a service. So this is things like Google App Engine, where you get a platform, you write an application, but the actual the backing store and the running of the machines is handled by the cloud provider. And the next highest level is software as a service, and this is things like Gmail, Google Apps, where you just interact with a pre-written application using a browser usually, or using some other sort of web technology. And you'll see other blah as a service, and this is generally just sort of adjuncts to these three things. So at each level, you sort of give more responsibility to your service provider, but you're also more beholden to your service provider especially for forensic investigations or any sorts of investigation purposes. So people can argue whether or not the cloud is great or whether it's terrible, but the simple fact is it's coming. There's nothing you can do about it. Sorry, that wasn't supposed to sound like a threat. Let's try that again. It's coming. There's nothing you can, oh, I can't, that still sounds like a threat. So tomorrow for data at rest, a large portion of data at rest will be entirely in the cloud. It might move locally for a little bit, but that'll be basically cache. And for some devices, there'll be no local data storage at all. So these streaming devices, the game console I talked about, none of those things have any local storage. For things that do have local storage, there'll be two broad categories. There'll be temporary, so just cache. This is what Chrome OS netbooks have. They have temporary cache on their local storage. And then there'll be longer-term archival backup. So this is things like data export from Google Docs. So the primary data store is still the cloud, but you can have a local export, which is like a snapshot in time of what was in your cloud application. For data in transit, volume and frequency will increase dramatically. Since all your data lives in the cloud, you need to manipulate your data, retrieve it, write to it. So this data passing back and forth will increase quite a bit. Larger cloud providers and cloud services will encrypt most or all of the traffic. It's usually fairly sensitive. So most of this should be encrypted. I think that's probably a given. Unfortunately, some cloud providers may not, especially if they're smaller cloud providers, sort of upstart, brand new technologies. Encryption is an afterthought, security is an afterthought. It always is, it always will be. You're not going to bake in security right from the beginning. That's just how the world works. So the possible lack of encryption of data being transited to and from devices into the cloud opens up the risk of interception for one. So either legitimate interception via wiretap or illegitimate interception becomes a risk at this point. But it also opens up the risk of tampering. So rather than just reading the data that's being transited, a malicious third party can manipulate the data that's being transited. So rather than having a great firewall where you just block content, you could possibly rewrite content to make it say, things are great, be happy, go to work. So tomorrow for data and execution, the majority of data execution will take place in cloud. So a local device will basically just issue a request. You tell the web application or the cloud application to do something. Processing happens on the back end on n thousands of machines, generates results, and sends it back. The device itself may not have any internal state of, or it may not keep state of what requests were made. It may not have any idea of what transforms were done on the back end on the data. And it may not log any of these things. On the remote end, the provider basically has a responsibility for all logging. So if tracing of execution and logging of things like this is important to you, it should be probably in your service contract with your provider, or it should be something that you should understand about the cloud services that you're using, what sort of logging is available to you. The things we gain from this advancement is you gain expertise through specialization. I was at a conference last year, and there was a cloud security panel, and somebody said, "Aren't you worried about all of your mom's data being at Google? Aren't you worried about Google having all of your mom's mail?" And he said, "I would rather have Google's security team in charge of my mom's mail than my mom in charge of my mom's mail." So. And that expands to any number of things, right? So you concentrate your data in one location, and then you build a fence around it, or you build a fort, right? This is classical defensive fortifications. This is the same sort of model used with firewalls previously, but this is being done with human skill. So you have your data protected by a small elite group of commandos. They're all sitting right there. We possibly gain damage control through segregation. So you can have your cloud services split up into various chunks, and you can firewall them off from each other, and then you can say, only this specific SOAP API can communicate to this cloud or whatever. This is not something that a lot of people do, but it's something that can be done using cloud resources. You gain known good base images. This is good for forensics because if you have, let's say, an infrastructure as a service cloud like EC2, you have 10,000 machines and they're all based on the same Debian base image, then you can quickly remove all of those files from the base image and then only look at files that have changed. This is sort of a double-edged sword because you can also get known bad base images. There was a problem recently with some pre-compromised images that were being used for base images. You can also get instant disaster recovery. So if your cloud gets wiped out, you can just spin up another cloud based on your existing data. And you can get disaster avoidance. So if you have cloud services in different availability zones, you can actually kind of avoid a disaster altogether. And for forensics, we can possibly, depending on the sort of cloud, this is probably more applicable to a private cloud, but we can freeze a crime scene instantly with virtualization and snapshots, which is pretty nice. It's not something that we really have the capability to do with traditional computer devices. So things we need to be ready for cloud forensics, or to perform forensics in cloud environments. We have to ensure the availability, integrity, and accuracy of logging, because for the most part, all of your forensic analysis is going to be boiled down to log analysis, especially for software as a service and platform as a service. Unless you specifically build something else into your application, looking at logs is going to be pretty much the extent of what you can do. You can actually test this via adversarial review, so you can do like a pen test against your application, see what logs are generated, see what logs are supposed to be generated. You should probably test this before you have to review these logs and use them. You can leverage disaster recovery and high availability features for preservation. So if you have a possibly compromised virtual machine, you can just snapshot that and then migrate everything over and then let it keep running while you examine the snapshot. One of the key things we'll have to do is understanding the physical location of data. This is something we talked about in an earlier session, because right now the sort of jurisdictional issues for cloud forensics, the kind of fallback is the jurisdiction is wherever the data physically lives, which is sort of an antiquated notion in this kind of cloud world, but that's how it is right now. And you also have to understand the level of incident response and forensic support that you'll receive from your provider if that's something that you need. For infrastructure as a service and for kind of private clouds, we can actually do some, I have an idea for in-cloud forensics. So rather than taking 2,000, 3,000 possibly compromised machine images and pulling them down, we can actually push forensics into the cloud. So you can kind of co-locate your forensic capability in the cloud. Because one of the things that the cloud providers, or the cloud gives us is elasticity for storage and processing, and those are the things we need for forensics. We need lots of processing and lots of storage, but we don't need them all the time. We only need them while we're doing work. And with virtualization, especially in a private cloud, we could theoretically do instant memory forensics and memory sampling. So you can write your memory image out to like a snapshotting file system, take periodic snapshots over time, and you have like basically core samples of memory. This is only if we have hypervisor access. I don't know of any public providers that give you like a full hypervisor to mess with. So this is my sort of theoretical for what we can do with in-cloud forensics in the future. So we have a single system in the cloud. It pops an alert, something bad happened. So we take a snapshot to some sort of block storage device, virtual block storage. We instantiate a forensic image in the cloud. So we have this is all happening in cloud. So we have a forensic examination workstation. We attach the storage to that. We do forensics. We find some things out. Okay, the system is owned. We have the following indicators. We scan the rest of our infrastructure for those indicators. this system's clean, this system's clean, this system's also compromised. So then we repeat this process for that system, and we continue going until we've scoped the entire threat. So basically, we're in the beginning of sort of cloud forensics and these sorts of changes that are going to affect us. But it's certainly not the death of forensics, and I think we'll still be able to continue to provide value and perform meaningful examinations, even given the limited scope of some of the things that we may have, especially in the logging area. That's all I have. If there's any questions, I can go ahead and take those now.